Hi all, let me take a look at a few problems in Achieve Section 3.9 with you. This video will cover problem 7, 15, 17, and 22. I was also asked for 23, but that's already on another video, so I'll just look at these four on this one. So of course this section is about the chain rule and logarithms and exponential function. This first problem does a good job of combining those facets of it. You'll see that you have the natural log of x inside of a function being raised to the fifth power and multiplied by 2, and then that's all inside of a natural log function. So you need to see that this is 1, 2, 3 layers. So there has to be 3 layers to my derivative. The first layer is derivative of any logarithm is always going to be 1 over whatever's on the inside of the logarithm. So I said, well, what's on the inside of it clearly is 2 times the group natural log of x raised to the fifth power. Then you have to say times the derivative of what was on the inside. And I look at what's on the inside, and what's on the inside is just that 2 times that group to a power. Well, you know, derivative of any group to a power, the power comes down in front. That's where the 10 came from. Times the group to the one lower power. This is layer 2 in my chain. Layer 3 comes from, well, the derivative of what was inside of that group. That's the derivative of the natural log of x, which is 1 over x. Then I just simplified my answer. And notice this one simplifies really nicely. You're multiplying by the natural log of x to the fourth. It was to the fifth power in the denominator. That's why you have 1 power of the log of x in the denominator. Of course, we have our factor of x in the denominator. And then the 10 over 2 reduced down to give me a numerator of 5. Fully factored, final form, and simplified answer. That's a good one. The next one asks me to look at an exponential function here, and specifically what we're doing with this exponential function is we need to find a tangent line when x is 1. Okay, so in order to find an equation of a line, I need a point and I need a slope. I'll concentrate on the point first. All I have to do is get the y value of the point, so I plug 1 into my exponential function. Gave me an exponent of 1 minus 2 plus 5. That's an exponent of 4. So I had to say, well, 4 to the fourth power is 256. That tells me that my coordinate that the tangent line goes through has to be 1, 256. Now I need to find the slope. And I can say, well, okay, in order to find the slope of this equation, I need to take the derivative and evaluate it at 1. So I know the derivative of any exponential function is always that exponential function, and then times the derivative of the exponent. Well, derivative of this exponent is going to be 2x minus 2 times the natural log of its base. So now when I tried to simplify that to find out what the derivative was evaluated at 1, I already knew when I plugged a 1 into the exponential portion, it gave me 256. So I went ahead and did that. But notice, the derivative of the exponent that creates this second factor, that's going to be a factor of 0. 2 times 1 minus 2. So it doesn't matter what the first or last term is. Any number times 0 is 0. So I just stopped as soon as I saw that second factor was 0. I said, well, my slope is 0. And I just made a comment here. It's unusual to get a slope of 0 when you're trying to find a tangent line, but we're correct in this case. That's what it came out to be. They just ask us to find a tangent line at a boring point. So this tangent line, it ends up being boring, like I'm saying, because whenever that slope is 0 and you try to plug this into your point slope formula, you say y minus y1, well, that's y minus 256. But if your slope is 0, your right-hand side's irrelevant. So you just say this is just going to be y is equal to 256. I'm not crazy about that one just because of the boring tangent line. So tangent line is just a horizontal line going through 256. Now the next one, it's also an equation of a tangent line. They give you r as a function of z here though. So my y value has to be represented by r of z, and of course my independent variable is z in this problem. So I can say, well, okay, it should be ez to solve out. I have a log base 11 of 2z squared minus 271. Find the equation of the tangent line when z is equal to 14. I first find the point. Plug in 14 for z. I said 2 times 14 squared. I know 14 squared is 196. 2 times 196 is 392. Then 392 minus 271 gave me 121 in there. And then that was nice to figure out because I know 11 to the second power is 121, and that's specifically what this is asking. Log base of 11 of 21 is literally asking you, what power do you have to raise 11 to get to 121? Answer is 2. So I know that the y value of my coordinate is going to be 2. So I have the coordinate 14, 2. Now I need to find the slope at that point. Slope, I have to take the derivative of my log function. Derivative of every log function in existence is 1 over what's inside the logarithm times the natural log of whatever the base of the logarithm is times the derivative of what was inside of that. And remember, when you're multiplying by the derivative of what's inside, that's actually going to go in the numerator, not the denominator. So the chain rule says to multiply by the derivative of 2z squared minus 271. Derivative of 2z squared is 4z. That 4z moved up to the numerator, and there's really nothing I can do to simplify that. But now I do need to evaluate that at 14 to get the slope, and that's what I did. You'll see 4 times 14. I already knew that this quadratic here would simplify to be 121. That's what I did up here. And then I have the natural log of 11. So this isn't really going to simplify other than just to say 4 times 14 is 56. We'll have 56 over 121 natural log of 11 for the slope. So I take that slope along with the point that I found earlier, plug it into your point slope formula. Y minus 2 is equal to your slope m times, in this case it's not x but it's a z, minus z1. Well, your z1 value is 14. Now instead of distributing that irrational slope, Achieve would prefer you to keep your answer exact. So I'll just leave my right hand side like this, move the 2 over, final answer there. The last one, I need you to remember here, this is not an exponential function. So the way I took the derivative in number 15, it's different in the last one here. In 15 you had a constant base variable exponent. We have rules for that. Derivative of any exponential function is that exponential function times the derivative of its exponent times the natural log of its base. Number 22, this is not an exponential function. We don't have a derivative formula for that. So the easier way to do it is just to go ahead and take the natural log of both sides. So I took the natural log of the left and right hand side, and then the reason that that helped out a lot is when I took the natural log of the right hand side, this exponent was able to come out in front. So I have 4e to the 7x times the natural log of x. Now you say, well, hey, that's excellent because I can just use the product rule to take the derivative now. That's what I did on the right hand side. On the left, I just said derivative of any logarithm is 1 over what's inside the logarithm times the derivative of what's inside the logarithm. On the right hand side, you can say, well, the derivative of the first term, derivative of any exponential function is that exponential function times the derivative of its exponent, that's where the 7 came from, times the second function, plus the first function, 4e to the 7x, times the derivative of the natural log of x, which is 1 over x. And then there's really not a nice way to simplify this. I just went ahead and factored it. And I also, at the same time, I had to solve for dy dx. So dy dx, I know I would need to multiply by y on both sides. Well, instead of putting a y on the right hand side, they want the answer all in terms of x. Well, we already know y is equal to this, so I just substituted that down in the place of y, x raised to the 4e to the 7x power. And now this came from recognizing that the two terms that were already on the right hand side both had a common factor of 4e to the 7x. If you factor that out, you're left with 7 natural log of x plus 1 over x. That would be a fully factored final fantastic form of your answer.